Good morning everyone, welcome to Sai Tutorials. So in yesterday's class we have discussed some of the concepts. So in the yesterday's class we have discussed some concepts like introduction to electric charges, conductors and charging by induction, introduction to electric charges, basic properties, and yes, we have discussed these little things. So in today's class we are going to discuss about conductors and insulators. So in this conductors and insulators. See, what is conductor? What is conductor? Then the substances, those substances which easily allow the electricity to pass through them. The electricity to pass through them. Those are called as conductors. See, in the lower classes, I mean in your high school sections, you have did some experiments like you are connected to some metallic pin and some battery and to the bulb, okay, and to the bulb. See, conductivity, conductance. See, the conductance means I have said those substances which allow the electricity to pass through them. See, those substances are metals, okay, and human beings also conduct electricity, and animal bodies and earth. These are the conductors of electricity. So these are some examples of electricity. See, let us take one example. I have taken here pin, okay, a pin. See, it is a type of metal. It is a battery. Okay, it is a battery. It is connected to a bulb. Okay, then I start the electricity. I switch on the bulb. Okay, if I want to switch on the bulb, I need to switch on to the current. Okay, if I pass electricity, some amount of extent of some electricity to these connections, see, the bulb will easily glow. Why it will glow? Because this pin is a metal. That's why it will conduct some electricity. See, you have experienced in some or the other way earthing agiti anta heltirtivi, houdri, earthing agiti anta heltirtivi. Yak agtirtೈತೆ anda because earth conducts some kind of electricity. ಆಮೇಲೆ ಶಾಕ್ ಹೊಡೆದಂಗೆ ಆಗ್ತೈತಿ ಅಂತ ಹೇಳ್ತೀವಿ because ಮನೆಯೊಳಗೆ ಲೈಕ್ ಎಕ್ಸ್ಟ್ರಾ ಏನಾರ ನೀವು ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಪಾಸ್ ಹೋಗುವಾಗ ಏನಾರ ಲೈಕ್ ಹಿಂಗೆ ಶಾಕ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಮಾಡಿರ್ತೀರಿ, ಹೌದಾ? ಸೊ ಆ ಟೈಮ್ ಒಳಗೆ ಏನಾಗ್ತೈತಿ ಅಂತಂದ್ರೆ ವೈ ಇಟ್ ವಿಲ್ ಹ್ಯಾಪನ್? ದಿಸ್ ಇಸ್ ಜಸ್ಟ್ ಬಿಕಾಸ್ ದ ಟ್ರಾನ್ಸ್ಫರ್, ಐ ಮೀನ್ ದ ಕಂಡಕ್ಟೆನ್ಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ. ಅಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಪಾಸ್ ಆಗೋದ್ರಿಂದ ಏನಾಗ್ತೈತಿ ಅಂತಂದ್ರೆ ದಟ್ಸ್ ವೈ ದೀಸ್ ಆರ್ ಕಂಡಕ್ಟರ್ಸ್. ನೌ ನೆಕ್ಸ್ಟ್ ವಿ ಗೋ ಫಾರ್ ಇನ್ಸುಲೇಟರ್ಸ್. ವಾಟ್ ಡು ಯು ಮೀನ್ ಬೈ ಇನ್ಸುಲೇಟರ್ಸ್ ದೆನ್? See, the opposite to the definition of this, those substances which do not easily allow electricity to pass through them are called insulators. These are called insulators, or it is also called as dielectric medium. See, dielectric means insulators means the substances, those substances which do not allow the electricity to pass through them are called as insulators. See, for example, let us take a rubber. Okay, rubber. See, instead of this pin, I am going to take rubber. It is a rubber. See, if I connect it to the rubber and switch on the electricity, I mean I switch on the bulb. See, it will not conduct any electricity because the rubber is insulator, that's why it will not conduct any electricity. So the substances which do not allow electricity to pass through them are called as insulators or dielectrics. So in this today's class, conductors and insulators we have discussed. So conductors means the substances which allow the electricity to pass through them are called as conductors. And the examples are metals, human beings, animal bodies and earth are some of the conductors. And in case of insulators, those substances which do not allow easily electricity to pass through them are called as insulators. So for example, rubber irbodu, plastic, these are some examples of insulators. So next we go for some basic properties of electrostatic properties of conductor. See, I have said conductor means which allow the electricity to pass through them are called as conductors. So then what are the some properties of the conductors then? So inside a conductor, any conducting material or any conducting medium, the electric field is always equal to 0. See, if I take for example any conducting medium, conductor, okay, it is conductor, any conductor medium, the electric field inside the metallic medium is always equal to 0. This is the first property. This is the first property of conductor. So inside a conductor, the electric field is always equal to 0. It is always equal to 0. Next, at the surface of a charged conductor, electric field must be normal to the surface at every point. See, I have said inside the material, inside the conductor, the electric field is always 0. Then what about the surface? Of the electric field? It is always equal to normal. I mean normal means perpendicular. It is always in the perpendicular or it is in the normal. So at the surface of a charged conductor, electric field is always be normal to that surface at every point. Next, we come for the electric potential. Electric potential is constant throughout the volume of the conductor. See, inside the conductor, the electric field is 0. At the surface, the electric field is normal to the surface of the conductor. While in case of electric potential is constant. It is constant throughout the volume, throughout the volume of the conductor. These are some of the properties of basic electrostatic properties of conductor. See, the basic properties are inside. If I take for example any conducting material or conducting medium, the electric field inside that cube, inside the material is always equal to 0, and the electric field at the surface of the any electric material is always normal to the surface of that conducting medium. And also electric potential is constant throughout the volume. Okay, the electric potential is constant throughout the volume of that conducting medium. Next, see, next we go for very important thing, that is Coulomb's law. It's a very important. It's a very important thing to learn in physics, that is Coulomb's law. Coulomb is one of the scientists who derived the definition of Coulomb's law, that is the electrostatic force of interaction between two electric charges Q1 and Q2 separated by a distance r and is directly proportional to the product of the charges and inversely proportional to the square of the distance between them and acts along the straight line joining the two charges. See, it will make some difficulties in while reading, but I will make you so ನೋಡಕತ್ರ ಏನಾಗ್ತೈತ್ರಿ ಅದು ಏನೋ ದೊಡ್ಡದೈತಿ ಏನೋ ಅನಿಸ್ತೈತಿ, ಬಟ್ ಐ ವಿಲ್ ಮೇಕ್ ಇಟ್ ವೆರಿ ಈಸಿ ಫಾರ್ ಯು. ಸಿ ಏನು ಹೇಳಾರಿ ಅವರು, ಇಟ್ ಸ್ಟೇಟ್ಸ್ ದ್ಯಾಟ್ ದ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೋರ್ಸ್ ಆಫ್ ಇಂಟರಾಕ್ಷನ್ ಬಿಟ್ವೀನ್ ದ ಟೂ ಚಾರ್ಜಸ್ ಆರ್ Q1 and Q2 in a straight line. Okay, in a straight line, they have said in a straight line. Let us consider this is one charge and this is another charge. Okay, let us consider this is one charge and this is another charge. Let us take it as plus Q charge and let us take it as minus Q charge. Okay, the electrostatic force of interaction between the two electric charges Q1 and Q2 separated by a distance separated by distance is ಹೇಳಾರಿ ಅವರ R ಅಂತ ಹೇಳಾರಿ. Separated by a distance R is directly proportional to the product of the charges and inversely proportional to the square of the distance. Okay, the square of the distance between them and acts along the straight line joining the two charges. So ಏನು ಹೇಳಾರಿ ಅವರ, force of interaction, Coulomb's law ಏನು ಹೇಳ್ತೈತ್ರಿ, force of interaction between the two charges, that is Q1 and Q2 separated by a distance R, is directly proportional to the ಪ್ರಾಡಕ್ಟ್ ಆಫ್ ಚಾರ್ಜಸ್ ಅಂದ್ರೆ ಏನ್ರಿ, Q1 ಮತ್ತು Q2. ಹೌದಾ, ಇದೇನಿದು Q1 and Q2. ನಾವೇನು ತೊಗೊಂಡಿವಿ, Q1 ಅಂತಂದ್ರೆ ಪ್ಲಸ್ Q ತೊಗೊಂಡೇವಿ, ಇದು ಮೈನಸ್ Q ಅಂತ ತೊಗೊಂಡೇವಿ. ಹಾಂ, ಆ್ಯಂಡ್ ಡಿಸ್ಟೆನ್ಸ್ ಇಟ್ ಈಸ್ ದ ಸ್ಕ್ವೇರ್ ಆಫ್ ದ ಇನ್ವರ್ಸ್ಲಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ದ ಸ್ಕ್ವೇರ್ ಆಫ್ ದ ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದೆಮ್ ಆ್ಯಕ್ಟ್ಸ್ ಅಲಾಂಗ್ ದ ಸ್ಟ್ರೇಟ್ ಲೈನ್ ಆಫ್ ದ ಚಾರ್ಜಸ್. ಸೊ ಇಲ್ಲಿಗೆ ಮುಗೀತೇನ್ರಿ ಅದು ಅಂತ ಕೇಳ್ಬೋದು ನೀವು. No. See, in the whole phenomenon, okay, Coulomb's law stated that F, okay, F is directly proportional to the product of the two charges and the square of the distance between the two charges, where K is a proportionality constant. Okay, the force is directly proportional to the proportionality constant proportionality constant, and its value is equal to K means 1 by 4 pi epsilon naught. So, whose total value is equal to 9 into 10 to the power of 9 Newton meter square per coulomb square. See, what is Coulomb's law is? The electrostatic force between the two charges Q1 and Q2 is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges. So, I have derived this one. And what is K? K is proportionality constant whose value is equal to 1 by 4 pi epsilon naught. What is epsilon naught then? Epsilon naught is permittivity of free space. What is permittivity? Epsilon naught is equal to permittivity of free space. Okay, epsilon naught is equal to permittivity of free space whose value is equal to 8.854 into 10 to the power of minus 12 Coulomb square per Newton per meter. Okay, epsilon naught is equal to permittivity of free space whose value is equal to, it's very important, 8.854 into 10 to the power of minus 12 Coulomb square per Newton per meter. Then its value is 9, K value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Okay, so what is Coulomb's law? The electrostatic force of attraction, the electrostatic force of interaction between the two charges, those two charges are Q1 and Q2. Okay, those two charges are Q1 and Q2. I have taken these as plus Q and minus Q. So, ಈ ಎಲ್ಲ ವ್ಯಾಲ್ಯೂಸ್ನು ಹಾಕಿದ್ರೆ ಏನಾಗ್ತೈತ್ರಿ? See, I have said the force of electrostatic attraction between the two charges, that is K, proportionality constant K, is equal to Q1 into Q2 divided by the square of the distance between them. Okay, this is the Coulomb's law. So, in a simplified manner, it can be defined as F is equal to, what is proportionality constant? 1 by 4 pi epsilon naught into, what is Q1 I have taken? Plus Q and minus Q divided by the square of the distance. See, or it can also be written as F is equal to, what is the value? What is the value of 4 pi epsilon naught? 1 by 4 pi epsilon naught is 9 into 10 to the power of 10 to the power of 9 into plus Q into minus Q divided by R square. This is the Coulomb's law. This is the Coulomb's law. See, in a vector form, I am going to tell you about in a vector form, how will you define it? So, in a vector form, I am going to have the two charges as like it is. Okay. This is Q1 and this is Q2. Okay. This is Q1 and this is Q2. The force of attraction between these two charges are written as F12 and this is F21. F21. Okay, then the distance between the two charges are written as R. In the vector form it is written as R1 2 bar. Okay, the bar on the above F is written because like this is it is a vector formation. Okay, vector ಒಳಗೆ ಬರಿಬೇಕಾಗಿತ್ತಂದ್ರೆ ನಾವು ಏನು ಮಾಡ್ತೀವಿ, we denote it as bar on the top of this force. Okay, then the force on Q1. Okay, first thing is force on Q1 due to Q2. It is force on Q1 due to Q2. It is written as proportionality constant as it is Q1 into Q2 divided by R square, but in the vector form force on Q1 due to Q2 it is written as R21. This can be written as equation number 1. Okay, force on Q1 due to Q2. Okay, force on Q1 L force agatitri Q1 ಮೇಲೆ ಎದಕ್ಕೆ ಆಗತೈತಿ, due to Q2. So this thing can be written as K into Q1 into Q2 divided by R square into R cap 21. Next, force on Q2 due to Q1. How can you write it is? How can you write due to Q1? How can you write it is K into Q1 into Q2 divided by R square into R1 2 K, because it is the force on Q2 due to Q1. Now here R cap 1 2 is a unit vector. Okay, it is a unit vector. See, if I want to derive in the vector form, I need some quantities. Okay, I need some quantities like Q1 and Q2, force R1 and R2, like that. So in a Cartesian coordinates or in a planar coordinates, I am going to derive like this. Okay, this is a x axis and this is y axis. Okay, it is a origin. So it is from origin to this thing is Q1. Okay, the charge is Q1 is moving in this direction and the charge Q2 here it is. Okay, the charge is Q2 here it is. The distance between the two charges is R. From origin to Q1 it is R1 bar and it is R2 bar. Okay, then the force on Q1 due to Q2 can be written as F12 bar is equal to K into Q1 into Q2 divided by R1 minus R2 bar whole cube into R1 bar minus R2 bar. While in the vector formation, we are going to write the force in this formation. See, this is a force on Q1 due to Q2 and this is force on Q2 due to Q1. So, Coulomb's law states that the force of an interaction between the two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between those two charges. So, this is all about the Coulomb's law. So, next we are going to define the term that is forces between multiple charges. Forces between multiple charges. This is also nothing but the principle of superposition. The principle of superposition is nothing but, it states that when a number of charges are interacting with each other, total force acting on a given charge is a vector sum of the forces exerted on it by all other charges. ನಾವು ಇಷ್ಟೊತ್ತನ ಏನು ಕಲಿತ್ವಿ, ಟೂ ಚಾರ್ಜಸನ್ನು ತೊಗೊಂಡು ಏನು ಮಾಡಿದ್ವಿ, ಕೂಲಂಬ್ಸ್ ಲಾನ ಡಿರೈವ್ ಮಾಡಿದ್ವಿ, ಹೌದಾ. ಸೊ ಈಗ ಏನು ಮಾಡೋಣ ಅಂತಂದ್ರೆ ದ ಮಲ್ಟಿಪಲ್ ಚಾರ್ಜಸ್, ಓಕೆ, ಮಲ್ಟಿಪಲ್ ಚಾರ್ಜಸನ್ನು ತೊಗೊಂಡು ಏನು ಮಾಡೋಣ ಅಂತಂದ್ರೆ ದ ಪ್ರಿನ್ಸಿಪಲ್ ಆಫ್ ಸೂಪರ್ ಪೊಸಿಷನನ್ನು ಡಿರೈವ್ ಮಾಡೋಣ. ಸೊ let us consider same Cartesian coordinates but in the 3 axes. This is x axis, this is y axis and this is z axis. So this is origin. The multiple charges is nothing but, let us take it as q1, this is q2, this is q3, this is q4, etc. Okay, multiple charges. The distance between the two charges for q1 is r1 bar, r2 bar, r3 bar, r4 bar for the multiple charges. Then what do you mean by principle of superposition is nothing but the forces, okay, the forces between multiple charges. So forces between multiple charges, here there are multiple charges are present here. So the interaction with each other, interaction with each charges is denoted as superposition. Principle can be derived as F1 bar plus F2 bar plus F3 bar plus F4 bar up to so on. This is a superposition principle of forces between multiple charges. See, this is the principle of superposition principle. So the forces between the multiple charges is also nothing but the principle of superposition. It can also be stated as when a number of charges, okay, when a number of charges like q1, q2, q3, q4 up to so on are interacting with each other, total force on a given charge, then the total force on a given charge is a vector sum of the force exerted on it by all other charges. Okay, this is the principle of superposition. This is the principle of superposition. Okay, have got this. The forces between the multiple charges is also nothing but the principle of superposition. So in the next concept, continuous charge distribution. Okay, you in the syllabus, see in the syllabus I have covered introduction to electric charges, conductors and insulators, charging by induction, basic properties of electric charges, Coulomb's law, forces between multiple charges is also nothing but the principle of superposition. Principle of superposition. Now we are going to deal with continuous charge distribution. We are going to deal with continuous charge distribution. See, continuous, okay, I have said that distribution of charges, okay, in one class, in yesterday's class I have discussed some of the properties and in that I have discussed some charges, okay, charges and the charge distributions, okay, how the distribution of charges will takes place like that, okay. In today's class, continuous charge distribution. What do you mean by continuous charge distribution? ಅದು ಹೆಂಗೆ ಆಗ್ತೈತಿ ರೀ, ಅದು ಯಾವ ಥರ ಮಾಡಿಫೈ ಆಗ್ತೈತಿ, ಅದು ಯಾವ ಥರ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಆಗ್ತೈತಿ ಚಾರ್ಜಸ್. ಲೆಟ್ ಅಸ್ ಟೇಕ್ ಇಟ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್. ಫಸ್ಟ್ ಥಿಂಗ್ ಈಸ್ ಲೀನಿಯರ್ ಇನ್ ಒನ್ ಡೈಮೆನ್ಷನ್. ಓಕೆ, ಲೀನಿಯರ್ ಇನ್ ಲೀನಿಯರ್ ಒನ್ ಡೈಮೆನ್ಷನಲ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಆಫ್ ಚಾರ್ಜಸ್. ದೀಸ್ ಲೀನಿಯರ್ ಅಂತಂದ್ರೆ ಏನು ರೀ, ಲೀನಿಯರ್ ಆಗಿರುವಂಥ ಇನ್ ಒನ್ ಡೈಮೆನ್ಷನ್ ಆಗಿರುವಂಥ ಎಕ್ಸಾಂಪಲ್ಸ್ ಯಾವ ರೀ? ಚಾರ್ಜ್ ಆನ್ ಅ ಲಾಂಗ್ ವೈರ್. ಓಕೆ, ಇಟ್ ಈಸ್ ಅ ಲಾಂಗ್ ವೈರ್, it is one dimension. Okay, it is one dimension. In this or a ring or a ಈ ವೈರ್ ಅನ್ನ ರಿಂಗ್ ಮಾಡಿದ್ರೆ ಏನಾಗ್ತೈತಿ? ರಿಂಗ್ ಆಗ್ತೈತಿ. ಸೊ ಇಟ್ ಈಸ್ ಅ ಒನ್ ಡೈಮೆನ್ಷನಲ್. ಸೊ ಇನ್ ಒನ್ ಡೈಮೆನ್ಷನ್ when the charge is uniformly distributed over a line or a straight line or a curved line, we call it as a linear charge distribution. For example, let us consider a long wire. Okay, let us consider a long wire of AB, length L, AB, and the length is L, on which a charge is distributed uniformly. So let us consider lambda. Okay, let us consider lambda is equal to the linear charge density. Let us take it as linear charge density. Okay, let us consider it as linear charge density. Here, see, linear charge density is nothing but charge by length. Okay, the charge by length. Now consider a small length. Okay, ನಾವೇನು ಮಾಡೋಣ್ರಿ ಅಂತಂದ್ರೆ ಒಂದು ಸ್ಮಾಲ್ ಲೆಂತನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡೋಣ in the long wire of AB whose length is small dl. Okay, whose length is dl. Then charge on the element of length dl. Then what is the charge of element on length dl? Is nothing but dq is equal to lambda into dl. This is equation number 1. Okay, the charge on the linear length of wire, that is dl, the small length, so we denote it as dq is equal to lambda into dl. Now electrostatic force of charge ಯಾವ ಚಾರ್ಜ್? q naught. Okay, q naught ಅಂತ ಚಾರ್ಜ್ ತಗೊಳ್ಳೋಣ. q naught is placed at a point p. Okay, ಏನು ಮಾಡೋಣ್ರಿ ಅಂತಂದ್ರೆ ಈ ಚಾರ್ಜ್ ಈ ಪಾಯಿಂಟ್ ಏನು ಮಾಡೋಣ ಅಂತಂದ್ರೆ ಕ್ಯೂ ನಾಟ್ ಚಾರ್ಜನ್ನು ಆಟ್ ಪಾಯಿಂಟ್ ಪಿ ಆಗಿ ತಗೊಳ್ಳೋಣ. ಇಲ್ಲೇ ಪಿ ಆಟ್ ಪಾಯಿಂಟ್ ಪಿ. ವಾಟ್ ಈಸ್ ದ ಚಾರ್ಜ್? ಕ್ಯೂ ನಾಟ್ ಅಂತ ತಗೊಳ್ಳೋಣ. ದೆನ್ ದ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ that point P is R. Okay, the distance of that point is R. Then the electrostatic force na in linear in one dimensional distribution ಒಳಗೆ ಹೆಂಗೆ ಡಿನೋಟ್ ಮಾಡ್ತೀವಿ ಅಂತಂದ್ರೆ it can be denoted as F is equal to, or the smaller ಏನು ತಗೊಂಡಿವ್ರಿ ನಾವು, ಸ್ಮಾಲ್ ಲೆಂತ್ ಅನ್ನು ತಗೊಂಡಿವಿ. ಸೊ ದ ಫೋರ್ಸ್ ವಿಲ್ ಆಲ್ಸೋ ಬಿ ರಿಟನ್ ಆಸ್ ಇನ್ ದ small form. Okay, dF bar is in the vector formation, it is denoted as dF bar. It can also be written as 1 by 4 pi epsilon naught the charge of a small length dq into the charge placed at point P, it is q naught divided by r square. In the vector formation it is r cube. This is the linear distribution of charge. It is a linear distribution of charge. This is the expression for the linear distribution of charge. This is equation number 2. So continuous charge distribution in the linear, in one dimensional form, it is written as when the charge is uniformly distributed over a line or a straight line or a curved line, we call it as a linear charge distribution. So in the linear charge distribution, we have considered the line wire AB whose length is L. So in that AB of length L, we have taken a small length dl. Okay, we have taken a small length dl. So the the charge on the linear charge density. The linear charge density, it is denoted as lambda. Now the small charge distribution, it is lambda into dl, of length dl. Okay, then the force, let us consider a point of charge q naught be placed at a point p, whose distance is r. The force of interaction, the force of uniformly charged distribution for the length dl, and the force df is written as 1 by 4 pi epsilon naught into the small length dq, and at a point p it is the charge q naught, and the distance of that small straight wire of length dl, it is denoted as r square. In the vector formation, it is r cap. This is all about the linear charge distribution or the one dimensional charge distribution. In the same way we have to take it for surface. Okay, surface distribution of charge. Surface in the sense 2 dimension. Okay, surface in the sense 2 dimension. When the charge is continuously distributed uniformly over a surface, we call it as surface charge distribution. We call it as surface charge distribution. In the surface, charge on a, example is charge on a membrane or a film or a plane sheet. Okay, or a plane sheet. ಯಾವ ಥರ ಆಗ್ತೈತ್ರಿ ಅದು ಪ್ಲೇನ್ ಶೀಟ್ ಮೇಲೆ? ಸೊ in the same way, let us consider a plane sheet. Okay, this is a plane sheet. This is 2 dimension. This is 2D, 2 dimension. So in that, the uniformly distributed charges are there. Okay, uniformly distributed charges are there, like this. Okay, then whose surface charge density, is denoted as sigma. It is denoted as surface charge density. Surface charge density, it is denoted as lambda. Okay, it is denoted as lambda. Now it is charged by area. We need to take charge by area, which is sigma. Okay, which is sigma. In the same way, ಒಂದು ಸ್ಮಾಲ್ ಸರ್ಫೇಸ್ ಅನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಳ್ಳು. ದಿಸ್ ಈಸ್ ಅ ಸ್ಮಾಲ್ ಸರ್ಫೇಸ್. ಓಕೆ, ದಿಸ್ ಈಸ್ ಅ ಸ್ಮಾಲ್ ಸರ್ಫೇಸ್ ಇನ್ ದ ಟೋಟಲ್ ಪ್ಲೇನ್ ಶೀಟ್. ಓಕೆ, ಇನ್ ದ ಟೋಟಲ್ ಪ್ಲೇನ್ ಶೀಟ್. ಸೊ whose length, I mean whose surface area is ds. Okay, whose surface area is ds, which is denoted, whose charge is denoted at a point p, that is at a charge q naught. It can also be written as, now the charge on the small surface is dq is equal to sigma into ds. Am I right? Sigma into ds. This is equation number 1. dq is equal to sigma into ds. Now the force acting on the small surface area, is denoted as dF bar. Okay, dF bar is equal to 1 by 4 pi epsilon naught. The charge on the small surface, it is dq, into at a charge q naught, which is placed at a point p, divided by r square. In the vector formation, it is r cap. This is the force of the charge distribution in the 2-dimensional surface area. Okay, in the 2-dimensional surface area. Have you got this? Surface in the 2-dimensional distribution of charges andre, when the charge distribution is continuously distributed uniformly over a surface, we call it as surface charge distribution. ಆ ಸರ್ಫೇಸ್ ಒಳಗೆ ಒಂದು ಸ್ಮಾಲ್ ಸರ್ಫೇಸನ್ನು ತೊಗೊಂಡು ನಾವು ಡಿರೈವ್ ಮಾಡಿದಾಗ ಏನಾಗ್ತೈತಿ ಅಂತಂದ್ರೆ we get the force on that surface. So in the same way, In the same way, 3-dimensional. We have considered 1-dimensional, 2-dimensional, and in the same way we have to consider 3-dimensional also. In the 3-dimensional distribution of charge, it is volume. Okay, in the 3-dimensional it is volume. When the charge is continuously distributed over a volume, then we call it as volume distribution of charge. Then we call it as volume distribution of charges. Here see the charge on a sphere, brick, etc. See, let us take it for example, the brick. Okay, the brick. It is a brick. Okay, it is 3-dimensional. Okay, it is a 3D. It is 3-dimensional. It is a 3-dimensional. So, let us consider any volume of a 3-dimensional form. Okay, let us consider a surface of volume V and whose charge is Q. Whose charge is Q, which is uniformly distributed over. Okay, I have said that, which is uniformly. The charge is continuously or uniformly distributed in the surface. Okay, then let us consider rho is equal to, here let us consider volume charge density. Volume charge density. Volume charge density. In the same way, let us consider a small unit, a small volume. Okay, let us consider a small volume or any cube. Okay, it is a 3-dimensional. Let us consider a small cube whose area, okay, whose volume is equal to dV. Okay, whose volume is equal to dV, which is whose charge is Q naught, which is placed at a point P. Then the force in this volume or the force in this 3-dimensional distribution of charges is denoted as dF is equal to 1 by 4 pi epsilon naught is equal to rho, the charge dq into q naught divided by r square into r cap. This is the force in the 3-dimensional form. Okay, this is the force in the 3-dimensional form. So, we have in the today's class we have learnt conductors and insulators and Coulomb's law. In the today's class we have discussed conductors and insulators and Coulomb's law and its properties, I mean its derivation and which is whose values and some examples and force between the multiple charges, that is principle of superposition, and some of the basic concepts related to this multiple charges and basic electrostatic properties of the conductor and linear charge distribution, volume charge distribution and surface charge distribution. These are all we have learnt in this today's class. So, in the tomorrow's class we go on study about the electric charges and which is presented in the syllabus. Okay. So, we have covered these things. These are all about the electric charges and fields. So, in the tomorrow's class we are going to deal with some electric field and electric field lines like that. Okay. So, I hope this will help you in one or the other way. So, thank you.